Hello and welcome everybody. Today we will be talking about the orders on the number line and also some reasons that we can use to create our statement and reason proof. So this is chapter 2, section 2 of our geometry book. So let's go ahead and get started then. So the first thing we're going to talk about are the numbers that are on the number lines and the sets of numbers that are going to represent them. So over here, you can see kind of like my generic picture of a number line that goes from negative infinity to positive infinity. And underneath it, these are all the sets that are inside the number line then. So the first one we talk about that is going to be, oh, sorry, not that right there. The first one we're going to talk about is going to be the real numbers. So that is used by the symbol with the R with a little bit of like a vertical line going through it. And that is going to be represented as any number that's on the number line. So if you can find a number, then that is going to be on the number line. That is considered a real number. So here are some examples. You have 4, 10, negative 8.1, 0, pi. All of those falls into the category. Okay. So if you can assign it on the number line, that's a real number. Now, from there, we can actually break it into 3 parts. There are the real positive number, so that's R with a plus. Then there are the reals that are negative number, that is going to be R with a negative. And then the one that does not fall into any of the categories would be 0 because it's neither positive or negative then. Okay. Now we talk about positive real number and negative real numbers. Are there such thing as imaginary? The answer is yes, but we're not going to talk about those right now because that's going to be another, another topic, another subject, another time. Okay. Next, after that, we have the integers, which is denoted by this letter Z over here with a small little tail. Integers are basically just kind of like whole numbers, and then also they're negatives too. So for example, negative 7, negative 2, we have 0, 5, 1,000, and so forth, okay? Then from that, the integer values, we can find the subset, what is known as the natural numbers. So those are going to be 1, 2, 3, 4, 5, 6, and so on and so on and so on. So the natural numbers are going to be integers that are not negative and also not equal to 0. So the easiest way to remember them is that they're just the counting numbers. So if you were playing, like, say, a game of, tag or who's it or whatever it is, hide and seek, that's the one, then you're going to be counting according to the natural numbers then, okay? The ones that we don't really talk about much, or this is kind of like new territory, would be the rational numbers. And rational numbers is defined as any number that is going to be on the number line that can be expressed as a ratio of 2 integers. So I think the terminology that a lot of people will use is fractions, but I do not like to use the term fraction because there are a lot of things that are fractions but are not considered rational. Note that here it says rational numbers are specifically ratios of 2 integers. So that means the numerator on top has to be an integer and the denominator in the bottom has to be an integer, for example, also. So here are examples of integers right here in both top and bottom where you have these rational numbers then. So negative 2/3, 7/10, 4, 0, 0 works because 0 divided by 2 is still equal to 0. And 62.7 also works because you can write it as a fraction where you have a ratio between 2 integers. Now, the fraction that are not ratio of 2 integers may be something like, say, pi divided by 4. So note that, yes, you do have a fraction, but you don't unfortunately have a ratio of 2 integer because pi, believe it or not, is actually a number that it cannot be, it's not an integer. Some people think that it is 22.7, but actually it is not equal to 22.7. It's very, very close to it. So that's why people use that as an estimate. But in reality, pi is a number that goes on forever and there's no end to it. So that is going to be crossed out for the rational number. And final item on the list of the number line for the sets, it is going to be the irrational number. So here we call it Q naught or Q prime, whichever one you want to call that then. So it's just a Q with a little dash above it to indicate that it's not going to be rational. And so we define this as any number on the number line that cannot be expressed as a ratio of 2 integers. So here are the examples of them. You have square root of 5, you have negative cube root of 2, and then we have that pi that we were just talking about, right? So those are all the sets that we have right now for on the number line. Now let's go ahead and talk about something called the field axiom. The field axiom are basically going to be those reasons that we're talking about earlier that you can use to write your proof. The terminology axiom basically means that it's so simple that you cannot really prove it. We really just kind of take it for granted because it's just logically well, it's that simple. So let me kind of show you what I mean, so then that way you'll understand what I mean by that. So for the field axioms, there are four that we can consider right now. First, we have the operation of addition. Then we have the operation of multiplication, and for each one we have the commutative property, and then we have the associative property. And I think if back in Algebra 1 you've heard of some of these before. So for addition under commutative, the rule that we have over there is the following: a plus b is equal to b plus a. So like I said, it's so simple that there's no way to prove it because, this is something that we take for granted. 3 plus 4 is equal to 4 plus 3. So, no objective about that. If you ask anybody out there that is at least of grade school, they'll tell you that, yeah, this is definitely true. Now, for the multiplication, it's going to be the kind of same idea. You have a times b is equal to b times a. So those are my two for commutative, for addition and multiplication. Now, for subtraction and division, unfortunately, they do not work for commutative because a minus b is not the same as b minus a. For example, 3 minus 5 is not the same as 5 minus 3. So there's your counterexample. And division is the same idea, right? 1 divided by 2 is not the same thing as 2 divided by 1, so therefore it's not commutative. For associative, this one is a little bit more complex, but it's still doable. We have a and then plus in parentheses b plus c, and that is supposed to be equal to a plus b in parentheses there and then plus c. So that's going to be associative for addition. Whereas for multiplication, you can probably guess it, it's going to be a times in parentheses b times c is equal to a times b in parentheses there, and then multiply by c. So the best way for me to kind of tell the difference between commutative and associative is that commutative is about moving, and there are only two variables involved, moving from left to right and right to left. Okay, so that's the, hence commute. Whereas associative, it is about grouping, and then there are three variables involved because what you're doing is you're changing where the variable, where the parentheses is located. So let me kind of write that up on top. So commutative is moving, okay, and then you have two variables. Whereas associative is looking at grouping, and then we have three variables. Okay, so that's kind of like my neat little trick to kind of help you memorize this. Okay, next one. These are also axioms because they are very simple for the most part. The reflexive property, that literally just says x is equal to x, right? You pick any number that's on the number line, x is going to be just equal to itself. I guess technically right above it, right? I really should say for all x, y, and z in the real numbers, okay? And another symbol for all right here is this upside down A over here. So if you ever see that, that means for all. So we're basically looking at just real numbers in this case. That works, that allows you to use these axioms. So as I said, first one is reflexive. That's not too bad. The next one, symmetric, says the following. If you have x is equal to y, then we have y is equal to x. So you can see how the symmetric property is pretty much kind of like the same idea as commutative, but except you don't have a plus sign or you don't have a multiply sign. It's just kind of swapping on the opposite side of the equal sign then, okay? And finally, for the transitive property, if you have x is equal to y and we have y is equal to z, then that means the result is that x is equal to z, okay? So yeah, those are basically the three simple axioms that we're talking about. Let's see. One easy way for me to remember this one right here, kind of like using the same trick as we have up there for the other field axiom, is that look at the number of variables that is involved for each one of these. Reflexive is one variable, okay, so one variable, whereas symmetric is two variables, And then for transitive, that's going to be 3 variables. So the way I memorize it is that you have R, S, T, and then 1, 2, 3. So that will, hopefully give you a better understanding or easier way to remember it in the future. Okay, this one is going to be the one that's a little bit harder to swallow because it's pretty new for a lot of people. And I think for some textbooks, they don't really explain it too well either. So let's go ahead and go through this one together. Closure. Closure is the other axiom that we're going to talk about right here. So when we talk about closure, there are 2 things that I need to consider. You need a set and you need an operation. So a set is basically all of these sets that we talked about on the number line right here. Okay, it could be any of those sets. And then the operation, well, that's going to be something like, say, addition, subtraction, multiplication, division, square root, cube root, and those are all operations. Now, here is how it works then. In our first example, we said even numbers are closed under addition. The question is true or false. Even numbers are closed under addition. What that means, the word closed, right? The word closed, because we're looking at closure, is that if you take any 2 even numbers and you add them together, will it still be an even number? Let me repeat it one more time. If you take 2 even numbers, here's where I'm going to decipher this. Take 2 even numbers, add them, will the result still be even? That's what the problem is actually asking for. Okay, so note, as we said, we're going to take the even numbers as our set and then addition as our operation, combine them together by saying, hey, if I take any 2 numbers from the set, add them, will the result be even? And the answer, you probably notice, is going to be true then. So that is going to be true right there. And let me go ahead and use blue because that's a little hard to see. Okay, let's try the next one. Odd numbers are closed under subtraction. So once again, that means if you take 2 odd numbers and then you subtract one from the other, will the result always be odd? Okay, will the result always be odd? In this case, unfortunately, the answer is no, right? And any time that it's false or it's no, remember in geometry, all we have to do is just give a counterexample. So our counterexample could be something as simple as, like, say, 3 minus 1 is equal to 2. So there it is. Okay. Now remember, when it comes to closure, the result, remember, that you're looking for when you combine those 2 letters together, or 2 elements together, and you add them or subtract them, the result always have to be back into the original set. Not sometimes, but all the times. Okay. So here, let's try another one. Real numbers are closed under multiplication. So once again, decipher what that means. Can you take 2 real numbers, multiply them, and the result will always be a real number? I think the answer is yes for that one. So that's going to be true. And then here's our last example then. Real numbers are closed under division. Is that true or false? Give you a couple of seconds to figure it out. Pause and try to check the answer. Okay. For this one, our answer is actually going to be no in this case. And the reason is, well, the number 0, right? If you look at that as our counterexample, we cannot have something like, say, 5 divided by 0, because 5 divided by 0 is supposedly undefined. Another counterexample, maybe we can have 0 over 0. Yes, you can technically pick the same numbers in the same set because, there's no restriction about that. Now, if you're wondering, 0 over 0, is that actually undefined? The answer is yes. That's something that we're going to delve into further on as you go into Algebra 2. And calculus is kind of like built all of that. But, if you're not sure and you don't trust me about the 0 over 0 thing, let's go ahead and ask Siri just in case. All right, I'm not going to ask you anything anymore. Well, there you go. 0 over 0 is going to be undefined. So just like 5 over 0. Okay. Now, let's go ahead and finish that part up right here. Hopefully these aren't too bad because you've probably seen them back in Algebra 1. Distributive property, that one is going to say the following. Let me go ahead and use a red pen so you can see it. You have A multiplied by, in parentheses, B plus C, and that's going to be equal to AB and then plus A times C. So, that's not too bad because you're just distributing the A to each one as a multiplication. And the last one, this one you haven't heard of before, is called trichotomy. So what's going to happen here is that you have two numbers in the real numbers, right? Again, remember the symbol right here. This means for all x and y that's in the real numbers. There are three things that could be true. Either x is going to be less than y, x has to be greater than y, or x has to be equal to y. So picking any two numbers, it has to fall into one of those three categories, and hence that's going to be trichotomy then. Okay. All right. So now the last part that we need for the proof right here, and I know this is a little overwhelming, so it might be good for you guys to actually copy this down and put it in the notebook somewhere for your own reference. Okay, so the last part will be the properties of equalities, and again, these are things that we're going to be using to write the proofs. So I just want to make sure that you have the proper terminologies before we start writing these proofs with these axioms over here. Okay, so for the property of addition property of equality, sorry, that's what it's called. And we simplified it or shortened it to APE for addition property of equality. Here's what it says then. So again, this is looking at real numbers, right? So if we know that A is equal to B, right? So if this part is true, then that means that A plus C is equal to B plus C. So note that all we did was just really add a number to both sides, and that's your addition property of equality. Again, this is something that you used back in Algebra 1, but you probably didn't really take note of the name of it, but now we're going to. Okay. So subtraction property of equality, so same idea. If you have A is equal to B, then according to subtraction property of equality, you can subtract the same thing from both sides. So A minus B is equal to, don't use B again because we used that already. So let me go ahead and erase that. Let's say A minus C, just like before, right? And then that's going to be equal to B minus C. Next, for multiplication, if A is equal to B, you can probably guess it. Then the result is that A times C is equal to B times C. And for the last one, if A is equal to B, then the last result is that A divided by C is equal to B divided by C. This is provided that, remember, C does not equal to 0 because remember what we just said and what Cookie Monster told me because I don't have any friends. All right, can all of this be applied to inequality as well? And the answer is yes, right? So taking all of what we have right there, what we can do is maybe something like this. If A is less than B, and C is less than D, right? There's the small little extra part. The inequality part will then say something like this. A plus C is less than B plus D. And there you go. Okay. Or you could add both sides the same amount too, or you could add a different amount so long as the right-hand side is bigger. All right, so enough talk about all of that. Now let's go ahead and see how all of these will work out when you try to write a proof. So here's an example of a simple proof using algebra that you can kind of like rely on to help you see how things work out. So given 3x minus 6 is equal to 15, I want to prove that x is equal to 7. Now, since you took algebra, you know how to actually do this, right? You can literally just do it on the side. And in fact, that's what I'm going to do then. I'm going to go ahead and do this on the side. So let's see, let me go ahead and write it maybe right here on the left-hand side. So 3x minus 6 is equal to 15. I'm going to go ahead and add 6 to both sides, and that would then give me 3x is equal to 21. Next, I'll divide 3 from both sides, so there you go, x is equal to 7. So no, I didn't mess up right there, so that's good. That right there, well, that you can use as your outline or your guideline, just like we did back in the logic section. So let's go ahead and start and write our statement and reason then. So here is going to be my statement. Okay, that's where you're going to do all the algebra. And your reason, well, that's where you're going to use all of these axioms that we just named in order to help us figure it out. Okay, so here we go. Number 1, and my lines just disappeared. So, well, we'll just kind of work with that. We start with 3x minus 6 is equal to 15. And if you remember, well, that's just given because we just literally took that off the top. Next, what we're going to do is we're going to add 6 to both sides. So that means it's going to be 3x minus 6. And then we'll go ahead and say plus 6. And for the other side is going to be equal to 15 and also plus 6. So for that reason, well, you probably saw it earlier and you remember it, is going to be the addition property of equality. Okay. Next, we're going to kind of clean this up a little bit. So we have 3x is equal to 21. So for step 3, we can go ahead and say simplify, because anything where you're just adding some numbers and subtracting some numbers, multiplying the number, cleaning it up basically, we'll just go ahead and call it simplify. Okay, so that falls into all that category. But as soon as you say you're going to do something to both sides, like say in the next case right here, we now take 3x and then 21 right there, and we're going to both divide both sides by a certain number, which in this case is 3. That right there is now one of those properties or axioms that we were talking about. That is the division property of equality. And finally, for step 5, that's going to now give us the x is equal to 7 that we're looking for. So that's going to be simplified once again. So if you remember, we said that these proofs, they're meant to be short. They're meant to be kind of like, simple so you can get the grasp of it. And they're not supposed to be more than like, say, 10 steps then. Okay, and if you do take more than 10 steps, try to see if you can minimize that. All right, so here is the big thing. Now we're going to have our very, very first theorem that we can memorize and use in the future. The thing about theorems is that it's basically something that we have to build, we have to prove, and once we prove it, we can use it from here on out. Well, technically, all of this stuff right here we can still use, but the theorems are the ones that we use most often, and that's what we're going to build the entire geometry off of. Okay, so here's our very, very first theorem. There's no name for it, so we'll just go ahead and call it our first theorem if you want. Okay, so here's what it says. If a is less than b, and by the way, again, we're talking about real numbers, is going to be greater than 0, then the result is that a is going to be greater than b. Pretty straightforward for the most part, right? Let's go ahead and maybe like say, put some numbers up there so you can kind of see how that works. Let's try with some real numbers. 5 minus 3, yeah, that's definitely going to be greater than 0. And if I have it, then according to this theorem, then 5 is going to be greater than 3. And so, yeah, that's true. So, yeah, it looks like the theorem works then. If you want to try different numbers, go ahead and by all means. But I think you can probably see how that works then. So now, let's go ahead and prove this then. So number 1, we're going to go ahead and write the given. A minus b is greater than 0. So that is just plain old given. Now, step 2, well, if you're thinking about what we've been doing so far, I'm probably going to do something to both sides, and that something is add b. So a minus b, we're going to go ahead and say plus c. Oh, sorry, not plus c. Ooh, careful about that one. How about plus b? I think that's a little bit better, right? Let's see. And then for the other side, it's going to be greater than 0, and you're also going to say plus b over here. And for this one, we're going to go ahead and say that it's the addition property of inequality because we have an inequality sign, not an equality sign. Okay, so be careful about that. Addition property of inequality. All right, well, according to what we've been doing so far, I think we're pretty much done at this point. We have a on the left-hand side because the b and the negative b cancels out. And that's going to be greater than b because 0 plus b is still equal to b then. So for that one, we simplify. And there we go. There's our proof. From here on out, we can actually use this theorem then. Okay, we build our sword. Now we can actually use it in the game. So that's the nice part about it. So next one, okay, this is going to be the last theorem of this section that we're going to talk about. And I'm going to show you what I mean by having to build a theorem and now we can use it from here on out instead of having to recreate the wheel every single time. So here's our second and last theorem for this section. Theorem 2.2, it says if A is equal to B plus C, and we know that C is going to be greater than 0, then the result is that A is going to be greater than B. Okay, so if a plus b is, if a is equal to b plus c, then c is going to be greater than 0, then that means that a is greater than c. So once again, I'm just going to go show you with some real numbers just to see that how it works. So let's say, for example, that 9 is equal to 8 plus 1. So you can see that c is going to be my a, 8 is going to be my b, and c is going to be my 1, which is going to be definitely greater than 0. According to the theorem, then that means that 9 is greater than 8. So yeah, that definitely is true then. Okay, so let's go ahead and write up the proof for this one, and hopefully you guys can follow along for this then, okay? So first of all, like we said, we're going to go ahead and start with the given. We are probably going to start with a is equal to b plus c because there's nothing much you can do with c is greater than 0. So we'll probably take that and leave it alone for the time being. Okay, and in terms of like how do you know where to start, well, that's just kind of like ingenuity for the most part. You have to kind of like guess trial and error, and since I don't want to like waste your time stabbing in the dark, we're just going to go ahead and go straight forward into what the actual answer is going to be. Okay, anyhow, that one we said it's going to be given, so that one hopefully is okay. And now, just like the last thing, we're going to go ahead and do the following. Let me go ahead and subtract b from both sides. So a is equal to b and then plus c, and I'm going to go ahead and subtract b from both sides as I said. Now, the reason for that is going to be subtraction property of equality. So that's going to be our step 2. So that now gives us the following. We have a minus b on the left, we have c that's on the right, and that is going to be just plain old simplifying every single time. Note that every time after we do some sort of property of equality operation, it's always going to be simplifying. So I think that's kind of like a common thing that we can go by. All right, here we go. Now, I think this is where we can probably use that next part, which says that c is greater than 0. For that one, that was also given to us. So if you want, we can go back and just go ahead and cross out what we use, just to get an idea as to what comes next. When it comes to proof, again, if you're ever stuck, always go back to the beginning and say, hey, what haven't I used yet? So then that way maybe you can kind of connect the dots. And that's what I'm doing right here. Well, seeing what we have, I do believe we can say the following over here. Step 5, we can say that a minus b is equal to c, which is greater than 0. For this one right here, we can just basically set them all equal to each other. So this is going to be called just substitution, okay? Or actually, we can go a little bit further. We really should say this is a transitive property, okay? I really should say that this is a transitive property. And the reason for that is we have 3 things on there. So let me just go ahead and write it down first. Transitive property. Okay, remember what we said earlier, RST 1, 2, 3, right? So here you'll notice that I have 1 thing, 2 things, and 3 things right there. So that's why I'm saying that it is a transitive property in this case. Well, I believe now we can just go ahead and cut the middleman, because if you look at what I have from number 5, and oh, by the way, if that helps, let me go ahead and write from step 3 and step 4 on the side, just so you can see where that came from. The final part is to go and prove what we want. We're going to cut the middleman and just go ahead and say a minus b is going to be less than 0, right? Just cutting the middleman right there. So that one, I'm going to go ahead and say transitive property one more time, because we're just cutting the middle part and just saying that the left-hand side is equal to the right-hand side, okay? Technically, I guess we don't really need part 5, but I'm just writing it in there so you can actually see what's happening. Okay, so we can actually put it all together if you want. So there it is, the last part, and I think you can probably see where this is going from here. We have now a minus b, and I am going to let's go ahead and add b to both sides then. So go ahead and say plus b, and then we're going to say plus b. And you still have that 0 on the other side. So this one is the addition property of inequality this time, right? And lo and behold, the very last step is a is going to be greater than b, and that's going to be your simplifying. Okay? Now, If you're wondering, well, what happened over here? Well, we did actually do the proof. This is the part that I want you to now think about, okay? Hey, if you remember from Theorem 2.1, we actually see that in Theorem 2.2, okay? Theorem 2.1 says that if you have a minus b is greater than 0, then a is greater than b. So that part is located right here. That part is located right there. That is going to be Theorem 2.1. So here's what that means. Instead of writing all of these extra steps in the end, here's what I can say. I'm going to go ahead and erase this and erase this. It's not that it's wrong, but I want to simplify and also reduce the number of steps. So here is my final step instead then. Step 7, we can now say that A is just greater than B, and the reason for that is Theorem 2.1, our first theorem. Okay, so you can see how this is actually nice because, like we said, we're not going to reinvent the wheel, but instead use what we have built already to reduce the number of steps, so then that way it'll be a lot shorter in terms of the proof. Later on, you're definitely going to be doing a lot more of this, and I'm going to go ahead and expose you to as much proof as possible, so then when the time comes and you have to do your own proof, you will be ready then. All right, so thank you so much.